Hello and welcome. Today we're going to be discussing section 5.3, which is on solving systems of linear equations by elimination. Our essential question for the day is how can you use elimination to solve a system of linear equations? Feel free to pause the video to take the time that you need to write that essential question down in your notes. To solve a system of linear equations by elimination, the idea is that we are going to be eliminating one of the variables. So for example, in any of the systems of equations that we've been working with, we have two variables that we're trying to solve for. If we eliminate one of them, then we can solve for the other. So if we just look at this example 2, if I eliminate one of the variables, I can then see the solution for the other variable. Now, of course, it's not just as simple as scribbling it out. There is a process to elimination, but that's the essential idea. We eliminate one so that we can solve for the other. To introduce elimination, we're actually going to start with step 2, which is add or subtract the equations to eliminate one of the variables. Now, in example 1, I have y is equal to 2, and we're also told that x minus y is equal to 4. Now, if I want to isolate x, I can go ahead and simply add y to both sides. If I add y to both sides, we notice that on the left-hand side, x is now isolated. And on the right-hand side, I have 4 plus y. But we can use the other piece of information that we know to help us here. I'm going to back up. I want to isolate x, so I'm going to go ahead and add y to the left-hand side. But I know that y is equal to 2, so I can add y to the right-hand side. Or, since y is equal to 2, I could also add 2 to the right-hand side. I can add y to the left and add y to the right. And that's exactly what I've done here. The only difference is that the y is now taking the form of 2 instead. Now when I do this, my negative and positive y are additive inverses, so they cancel each other out. And I have x on the left is equal to 6. And we were able to solve for x by eliminating that y term. Another way that we can write this, if I back up, is to add the entire left side of this equation to the left side of my second equation. So I'm going to add y to the left, and I'll line up my equal signs and add 2 to the right. Because y and 2 are the same thing, so I can add y to the left and 2 to the right. It just looks a little bit different, but they're actually equivalent. Now my y's are additive inverses. I have x on the left is equal to 6. Now this way that I've just shown you is going to be how I show elimination from this point forward. It's a little bit cleaner and easier to follow the steps of elimination as opposed to what I had written before. Now in number 2, my goal is to eliminate one of the variables. Now if I look at the left-hand side of each of these equations, I notice that if I add these two left-hand sides together, the y's are additive inverses, so they're going to cancel each other out. So I'm going to go ahead and do that. I'm going to take this entire left-hand side of my equation and add it to the left-hand side of the equation above. So doing so, when I add these two together, I have x plus y plus x minus y. And when I combine like terms, I have 2 x's. But the plus y and the minus y are additive inverses, so they cancel each other out. Now we could, on the right-hand side, add x minus y to the right-hand side of the equation above. But that really doesn't help us. That doesn't eliminate either of the variables. We still have a y in our question if I do that. But I have to add the same thing. If I add x minus y on the left, I have to add x minus y on the right. But instead of adding x minus y, we know that x minus y is equal to 2, so I can add that 2 to the right-hand side, and I get 10 plus 2, which is 12. And now I can divide both sides by 2 to solve for x. I find that x is equal to 6. Now, of course, we're not done because we need a complete ordered pair. I didn't finish number 1 either. We'll go ahead and finish number 2 all the way through. If x is equal to 6, we can go back and plug that in. If x is equal to 6, then x plus y is equal to 10. I'll input that value of 6 that we found. And solving, I find that y is equal to 4. So our ordered pair here is 6, 4. This is the point where those two lines cross. Going back to number 1, we have x is equal to 6, and we know that y is equal to 2, so our solution is 6, 2, and this would be the point where the two lines intersect. Example 1. We're going to solve the system by elimination. The first thing I'm going to look for is I'm going to make sure that both equations have an additive inverse with the other. Additive inverse means opposite terms. So these x's are not opposite terms because when I add them, there's going to be two x's. Additive inverses means when you add, things cancel out or you get 0. When I look at positive 3y and negative 3y, these are opposite terms, so they are additive inverses. So I'm going to go ahead and simply add x minus 3y to the left-hand side of my equation, and I'm adding x minus 3y also to the right-hand side of my equation, but that x minus 3y has the form of 16. Because these are equal to one another, we can add x minus 3y to the left and 16 instead to the right. So doing this, adding vertically, x plus x is 2x, positive 3y and negative 3y add to 0, and on the right-hand side, negative 2 and positive 16 add to positive 14. Dividing by 2, I find that x is equal to 7. Now, of course, we're not done yet because we're looking for the point of intersection, and a point has an x and a y value. So I need to find the x and the y value where these equations cross. So I go back to my original two equations, and I pick one of the two to substitute my x value. I'll go ahead and pick the first one. X plus 3y is equal to negative 2. X plus 3y is equal to negative 2. We know that x is 7. So now I solve. I'll go ahead and subtract the 7 from both sides. And I have positive 3y is equal to negative 2 minus 7 is negative 9. Dividing by 3, I find that y is equal to negative 3. So my x value is 7 and my y value is negative 3. So the point of intersection is 7, negative 3. Go ahead, take a moment to please pause the video and try doing just number 1 and 2 on your own. Number 1 already has additive inverses, so if I simply add, the y's are inverses, so they will cancel, leaving me with 6x on the left, and on the right I add 9 and 21 to get 30. Dividing by 6, I find that x is equal to 5. Now, of course, we do still need to solve for y, so I go back and I plug that into one of the two equations. I'm going to pick the one where the y value is positive. So I know my x value is 5. I go ahead and I plug in my x value of 5 to this equation. So 4 times x, which is 5, plus y is equal to 21. Simplifying, 4 times 5 is 20. 20 plus y is equal to 21. Subtracting that 20 from both sides, y is equal to positive 1. So I have my x value of 5 and my y value of 1, so the point of intersection is the point 5, 1. Number 2, I have additive inverses of negative 5 and positive 5, so I can go ahead and add the left and add the right. On the left, the x's are now additive inverses, so those cancel, leaving me with 3y. And on the right, I add 13 and negative 1 to get 12. Dividing by 3 on both sides, I find that y is equal to 4. Of course, I need to find x. I'm going to plug this in to the most simple equation. I prefer the second one. So I have 5 times x plus y is equal to negative 1, and y here is positive 4. Subtracting 4 from both sides, I find that 5x is equal to negative 5, and dividing by 5 on both the left and the right, I find that x is equal to negative 1. So my x value is negative 1 and my y value is positive 4, giving me a point of intersection that is negative 1, 4. Now for number 3, you might notice that we don't have additive inverses. 4y plus 4y is 8y. Those don't cancel each other out. So what I'm actually going to do here is I'm going to change one of the equations so that I do have additive inverses. I'm going to take this whole second equation, or the first equation, whatever your preference is, and multiply by negative 1. I'll go ahead and multiply the first equation instead. When I multiply the left side by negative 1, I'll distribute. And if I multiply the left by negative 1, I have to multiply the right by negative 1. When I do this, I've got negative 3x. Negative 1 times 4 gives me minus 4y is equal to positive 6. So I've changed that first equation by just multiplying everything by negative 1, and now I do have additive inverses. So I'm going to focus on now my new system of equations. If I add them together, the y's will cancel. 7x minus 3x is 4x. Negative 14 and positive 6 simplify to negative 8. And dividing by 4, I find that x is equal to negative 2. If we go back and plug that in, we can plug that into any of our 3 equations, the original 2 or that new third equation. Either way, when you substitute and solve, you will find a y value of 0, giving you the ordered pair negative 2, 0. The last example that we have today is going to be just a little bit more advanced. If we notice in this example, none of my coefficients match. So what I need to do is multiply so that I do have those additive inverses. I think the easiest thing to do is to force the x terms to be additive inverses. So if one of them is a negative 6, then I want this other term to be a positive 6. So I'm going to force that to happen by multiplying by a negative 3. That will force this first term to be a positive 6. But if I multiply the first term by negative 3, I have to multiply everything in the entire equation by negative 3. Distributing, I have 6x. Negative 3 times negative 4 is positive 12y is equal to negative 42. Now we use the first and the third equation to solve this system. Go ahead and take a moment to pause the video and see if you can solve this system by yourself. Solving this system, I found the solution 6, negative 1. Feel free to pause the video to compare my work to yours. Thanks so much for watching and have a great rest of your day.